Okay, I'll do my best. So thank you for inviting me here. And those of you who have problems with the Dutch pronunciation of Peter, just say Peter. It's fine. So I'm facing a similar problem as Diana mentioned, that I'm not all too sure about your background. So what I will do is first today slowly introduce you to the language of function fields. So I'm assuming you all have had some kind of course in algebraic geometry. That language is very similar, intuition is the same, but nonetheless I want to run you through this. So this will take me today, maybe also some part next lecture. And then I'll also slowly go over to what can be done there in connection with coding theory. And I'll finish this week by talking about some decoding algorithms, but I'm not going to say what that is this time. So the main algebraic primitive that I will need later to construct codes, they are algebraic curves. So this is already a huge restriction. It doesn't mean that it doesn't work for algebraic variety in higher dimension, it's just that that is the case that is best studied. So algebraic curves, well, if we just make a very simple picture of an example, we just have something like this. And for me, I was just thinking about the prime ideal in some polynomial ring, and the prime ideal will define an algebraic curve. So this F is just any field. Later it's going to be a finite field, but for now anything goes. So in this picture I'm just assuming we're talking about real numbers. Now associated to such a prime ideal we have a coordinate ring which is just the quotient modulo this ideal. Now since this was assumed to be a prime ideal, this is going to be a domain, so I can also take this field of fractions. So let's say Q for quotient of this coordinate ring. Yeah, so given a curve, we automatically are led to a function field in this way. And this function field looks like it's only going to be defined if I really talk about affine curves, but you can also do this construction for projective curves. Now, the question is, how is this correspondence? Yeah, so given a prime ideal in some polynomial ring, we get a function field. But what about the reverse inclusion? Well, it turns out that that is a bit more subtle, because if I look at a similar construction, let me write it down correctly, like this. Then I look at this ideal, it would over the reals look like parabola, like that. And it turns out that the function field down here is the same. If you do this construction, then you will get another function field. So let us call this curve C2, this curve we call C1. Then the function field down here, let me abbreviate this as FC1. And here I would get another function field, and they are actually the same. And to see how this isomorphism goes, let us just think of this as being generated by two elements, x1, x2, satisfying this polynomial equation. Yeah? So that is equal to 0 if I replace capital X by small x's. And then here I would have in a similar way generated by this, small y and small y1 and small y2. And then you can see that these two are isomorphic. And how do you do this? You just send x1 to y1 and x2 to y1 times y2. And you can show that this is going to be a field isomorphism. So what I really did in the geometric sense is I blew up the singularity. But the point is, what is going on here is that we have a map on the geometric side of things, which just sends a point on this curve, alpha beta, is sent to alpha times beta, like this. So also on the curve level, we see that something happens. So on the function field level, we get the same field up to isomorphism. Up here, we get something that's called birational equivalence, because this map is nearly always invertible. As long as alpha is not zero, we can also compute its inverse. And that is what is going on in general. So function fields, you lose some of the geometry of the starting curve, but not too much. It's just up to birational equivalence. And so let's just look at one more example here, because here, if you look at this equation, this just means that this y1 and y2 satisfy an equation, namely we get that y1 is equal to y2 squared minus 1. That is simply from the definition of this construction, the way it is written down here, these two variables will satisfy this equation simply because that polynomial was in the ideal. So it seems that this function field here, well, there's really no need to write down y1 here because you can express it in y2 already. So we in fact get a third isomorphism of fields. We can just write this field here in this way as f of y2. And again, there is a geometric consequence of this, because it just means that we can identify this parabola with a line. And what do? You just send an element beta to a point on this curve, namely beta squared minus 1 beta. Yeah, so what I'm trying to say is that these isomorphisms on the function field level give you also information about the curves, and vice versa. Now in general, if you don't have equality of function fields but an extension, you still get a geometric picture, but then you get a proper covering, not just a birational equivalence, or in this case isomorphism, but some kind of covering. So that is the geometric intuition behind function fields. Now the story runs a little bit deeper than this, because it turns out that in the theory of algebraic curves, you have a very nice property, namely that any curve, for example this one, is birationally equivalent with a non-singular curve. In this particular example, we have seen which one. And this is always the case. Given any curve, you can find, up to birational equivalence, a non-singular curve. And this is also true if we talk about projective curves. Moreover, it's not just that it exists, it is unique up to isomorphism. So if we're thinking about function fields, what we really can think of is just a non-singular projective curve, smooth curve. That is what is going on. So a non-singular projective curve is somehow the same thing as a function field, up to isomorphism. And that is the essential theme. Now, then a question is, okay, given a function field, can you somehow describe this non-singular curve from there? Not using geometry immediately, but just can you, in an algebraic sense, describe what this non-singular curve is? In particular, can you describe the points on this curve? So, this is what function field theory is about. Now, I think historically, the way many of these famous people thought about this was using function fields. So, for example, Helmut Hasse, he wrote papers on the function field. So, Chevalier has a book about function fields. Doering has function field theory in his publication. So, this is where it came from. And then, slowly it became superseded by the Grothendieck approach. But it turns out that for the purposes of coding theory, it's still nice once in a while to think in function fields. And this has become somehow tradition. So as a reference for this first part of my lectures, you can take the book by Henning Stichtenoot. It's called Function Fields and Codes. But in a sense now I can just start over. I will forget the geometric picture, although it's in the back of my mind all the time, and I will refer to it. But I can now just simply start by defining what a function field is, and from there build up the theory to see how we can describe the associated non-singular model somehow, without mentioning that explicitly. So, let me then start with the definition of a function field. So what we need is some kind of field of definition, just as we had before. So we have some fields, and then an extension field of f. So let me give this name. An extension field, capital F, of this field of constants, as it is called, f, is called a function field if so it has to be a condition, because what we need is somehow that the dimension fits. So how to fix that? Well, we just say we need some element x in the function field such that so the extension of this is a subfield. The subfield generated by the field of constants and this element. This has to be finite. That somehow captures that it is a, this nearly captures that it is a one-dimensional thing, a one-dimensional object. The only thing that could go wrong is that this x is actually algebraic over this other field f. And so that is the second condition. 2, this x is transcendental over the field of constants. So those two conditions capture the essence of what is going on. So the dimension is 1, and we can also say that since we have seen up here already that such a function field, we can think of it as corresponding to a line, a projective line if you wish. And then this here means we have an extension of that, so we have some kind of covering of a projective line. So really we can think of this as a curve. So this is a formal definition of a function field. Okay, just some assumptions this week. So I'm going to assume in the first place that this field f, I don't want it to be too complicated, so it has to be a perfect field. A perfect field, that means that any finite extension of this field is a separable extension. Yeah, so in characteristic 0, this is not a condition at all, but in positive characteristic, perfect really means something. It means any finite extension has to be separable. So I want to put this condition because what I am going to look at later is when this is a finite field. And finite fields are also perfect. So the important classes for me are finite fields, and they satisfy this assumption. And the second is that so-called full constant field of f is f. And just what does that mean? That means that if I would take some algebraic closure and I look into a field containing both this algebraic closure and the function field, then I would just get f back again. Another way to say it, if I pick any element from the function field that is algebraic over the constant field, it's actually already in the constant field. Now those are our two assumptions. Okay, so this all is just reformulating the notion of curve. So now remember what I want. Somehow I want to describe now the structure of a curve, especially a non-singular one that we know exists. Yeah, so what we want to do is now capture the essence of points on a curve in an algebraic way. And the basic notion is the following. So what we say is that we're going to look at subrings of this function field f. And there's a special kind of subrings, they're called valuation rings. And so there are two conditions to satisfy. First is, it cannot be too small, we don't want only the constant fields. And it may also not be too big, we don't want the entire field, the entire function field. And in the second place is that it is somehow maximal, and that means that if I pick any element from the function field, I want that the element itself is in the ring or its inverse. Now this seems to be coming out of the blue, but in fact we have to remember, what are we trying to do? We want to capture points. And what we're going to do is, you have to think that we try to describe points by describing exactly the functions defined in a point. So if you know all the functions that are defined in a point, this will turn out to be the right object to look at. So if we pick any point on a curve, a non-singular curve here, and we look at any function in this function field here, well, two things may happen then. It may either be defined in this point, or it may have a pole, as it is called there. And the function, the subring of functions that are defined in a particular point, those are the things we're looking at here. Those are the valuation rings here. Yeah, so if we think about this, yeah, this property is then all of a sudden natural, because if we pick a function, either it is defined in it, or it has a pole, but then its inverse is defined there. Yeah, so then this property is automatically satisfied. So that is really what we are looking at here. Okay, so then start thinking about properties of such valuation rings. Well, there are several worth mentioning, but one is that it is a local ring. So what does that mean? That means that it has a unique maximal ideal. So say P. And this unique maximal ideal has some further properties. If we would look at the intersection with this, it's going to be, sorry, just F, it's going to be 0. So what I'm trying to say is, what is this P? Yeah, so remember this ring is like all the functions defined at a specific point. Well, what is its maximal ideal then? All the functions that are 0 in this point. Yeah, so here that this intersection only gives O is because you can think of this ideal as all the functions that are 0 in a specific point on a curve. Yeah, and then this has to be the case. And moreover, this P is in fact a principal ideal. So you can generate it by one element like this. And this here, just to tell you, you don't need to know it, but what is really happening here is that you use that point we would be looking at is non-singular. Otherwise we would be in trouble here. Yeah, but we don't need to think about things like non-singular if you don't want to, because this is just a definition. From this definition, this will follow. Okay, and then the fourth thing is that from this property that this P is a principal ideal, we can derive that any element from the function field can be written down in a particular way, namely you can write it as t to the n times u, where n is some integer and u is an element from the units of this ring. Yeah, so this has to be read in the following way, that once we have picked this generator, then any element can be written uniquely in this way. Okay, so far what I've done is somehow try to model the kind of rings that would occur on a non-singular curve. Here is the definition, and then these rings are local rings, have a unique maximal ideal that is principal, and that gives rise to a way to write elements down, like here. Okay, so what we then now can do is define something that is called the place of a function field. So what is it? It is the maximal ideal of a valuation ring of the field F. Yeah, so we have a function field. P is a place if it is the maximal ideal of some valuation ring of F. And this P is going to play the role of points. Even the notation P suggests this. But it's called a place instead of that. Yeah, and we may as well give this valuation ring a name. So let's call it OP. So this valuation ring we call this OP. I want to show that given P, there's exactly one valuation ring in which it is the maximal ideal. So we may as well incorporate that in a notation. So an element such that this P is T times OP, it was a principal ideal after all. This element is called a local parameter. Okay, so this is in a nutshell a way to define places which are analog to points in a more algebraic way. Are there any questions up to here? Nothing? Okay, then set of all places we denote by P of F. Now I think it is time to look at an example. Yeah, well, certainly this P is borrowed from the projective world. That is why we have it here. So let us try to see again what happens in this case that we just saw, the function field of a line. And so what happens if we take the easiest possible function field? So we pick any transcendental element x, we form this field, and what happens in that particular case? It certainly is a function field, and yeah, it is called a rational function field. So let us see if we can describe some places here, as well as some local rings OP. So maybe it's easier to start with that. So what I will do is I will pick an irreducible polynomial. Yeah, so since x is transcendental, this is a polynomial ring in one variable, and let us take an irreducible polynomial from there. And it turns out that associated to such an irreducible polynomial is a place. So let me first write down what a local ring would be. So the local ring we can construct from here are all the expressions from this function field. So they are just quotients of polynomials. And then there is a demand that this P of x is not allowed to divide G of x. Now leave it as an exercise that this is a ring, and also that it satisfies these conditions on a federation ring. It's not difficult at all. So this is in fact a federation ring of the rational function field. So these irreducible polynomials, well, you see here that it's going to be a slightly different direction now. So if we imagine that this F is an algebraically closed field, let us say C, then all irreducible polynomials just look like x minus a constant, x minus alpha. Now in that case we can clearly see a bijection between points on the line and irreducible polynomials. Yeah, a point on the line, we pick one, alpha, the irreducible polynomial belonging to it is x minus alpha. So in case this is algebraically closed, we have a very clear one-to-one correspondence between points on an affine line and places of this type in the rational function field. So there we see exactly what is happening. But if this F is not algebraically closed, say Q or a finite field, then some more arithmetic is coming in. So this is kind of a mixture then of arithmetic geometry and field theory. So in that case, this is a completely different picture all of a sudden. And just for those who know that, you can think then of places as an orbit under the absolute Galois group of this field. That is a way to think about it. But anyway, here we have a number of places in this function field. And the real question is this all? So if we just imagine again that this f are the complex numbers, well, I just told you we have all the points on the affine line covered by this irreducible polynomial, but if we miss one point, right? So we have on a projective line, so to say, a point at infinity. So we're missing one. And it turns out that also here in this description we are missing one important place here. Yeah, just to complete this story, so the place belonging to this is just the ideal generated by this polynomial P of x. Now to see which one is missing, this may be easiest to first describe the places that we know in a slightly different way. So we still have here some properties of the local ring of a place here, and in particular here we have still this way of writing an element down. Now it turns out that a place P of the function field f place P gives rise to a valuation, in fact a discrete valuation from f to z. Yeah, so this comes very close to what Diana was talking about in the previous lecture about valued fields. So for any place, I'm saying we get a discrete valuation. So how to define it? Well, in the first place we are going to say the element 0, which he excluded, makes sense, but let us just move that to infinity. Okay, that is fine as long as I add it here in my image space as well. So this is just to take care of the 0, but then what is important is that this phi of z is just n if, just as above, this can be written like this. Yeah, so this p is t times op, and u is an element from the units of this ring. Now we just said there is a unique representation of this form. Well, okay, in that case we may as well map that function to this exponent n. And this gives you a valuation. So all these axioms that Diana also mentioned are satisfied. So not going to write them down again, since she already did that, but one that is important is this one. That the valuation of a sum, let me just add a p here, the valuation of a sum is larger than or equal to the minimum of these two parts. And this is what we call the triangle inequality. So why is this called the triangle inequality? Because that is something you may have seen where you talk about absolute values. But valuations are very closely connected to absolute values, because this Vp gives rise to an absolute value. which we can define as, we just pick some constant c to the power the valuation of z, and this c cannot be arbitrary, but some number between 0 and 1, some real number satisfying this. Then it turns out that this really gives rise to a norm, satisfying all the usual axioms for norms, and in particular we get that the norm of x plus y is supposed to be less than or equal to the sum of its norms. This is one of the axioms a norm has to satisfy. In fact, using this you get an even stronger statement, namely that it's less than or equal to the maximum of these two. So it satisfies even a stronger property. Now the way this theory developed before it was unified by the scheme approach was that there were a lot of different people using a different language. So these places and valuation rings in function fields, that was one approach. And then there was an approach by, among others, Zariski, using valuations. Yeah, so it turns out that a place gives rise to a valuation, but it's also the other way around. Given a valuation, you can actually find the valuation ring of the function field and then a place after that. So it is really a two-way thing, an equivalent description of the places. So let me then go back now with that knowledge to this example here. So I take a rational function field again, and what I'm going to do now is say, okay, but see, what I can do, I can define a valuation from this f to z to infinity, and what I can do is, well, as usual, 0 is mapped to infinity, but then, and now I really use, I am in the case of a rational function field. What about sending a fraction of polynomials like this to the degree of g minus the degree of f? And it turns out that this is a valuation. Please check that. Yeah, so now all of a sudden I have a new one, and just comparing it with the valuations that you would get from these ones, you see it's really a different one. So I have one more valuation, and let me say the corresponding place, P infinity. What is it? Yeah, it is really all the fractions f over g, such that the degree of g is larger than the degree of f. Yeah, so why is this a natural choice? So if I would, from the valuation, want to reconstruct my place, yeah, what I need to do is I need to pick all z's where this exponent is at least 1. Yeah, this p is just all multiples of t. So from the valuation, I can reconstruct P by choosing all elements with positive valuation. And that's what I'm doing here for this particular example. So there's one more here, P infinity, and that completes the whole picture. So this point of infinity on the projective line that was missing, it's this place here. And one can show that there are no more. Yeah, so this is a complete description. You get ones from irreducible polynomials, and then one more, namely this P infinity, and there's nothing else. Now maybe some of you have had some number theory, especially from number fields. So there's a similar theorem for Q. Yeah, if you look at the rational numbers, and you try to make that into a valued field, or rather the field with a norm like this, then it turns out that there are two possibilities. So one possibilities are these p-adic valuation that Diana mentions, and then it turns out there's one more, which is the usual absolute value on Q. And then there's a theorem by Ostrovsky that that's all. And here we have a similar picture. We have the prime elements from this ring. So instead of Z, we take this ring. Yeah, so if you would, this is the quotient field of this polynomial ring. So if we would try to generalize this to Q, it makes sense to put the ring of integers there. So we have the prime elements from the ring, which gives you p-adic evaluations. And then there's one at infinity. Now the special thing about function fields is that this extra one has the same structure again. It's again coming from a discrete valuation. That is not true for Q. But for function fields, there's essentially only one kind of absolute value, namely the ones coming from valuations called ultrametrics. Okay, so there are a few more things I would like to tell you, so we get some more notation in place. Maybe I'd better not use this one. Okay. So they are called function fields, these objects. So that name suggests that you can evaluate those functions somewhere. So that is something that is still missing. So if we have a curve, functions on a curve, we can evaluate them at points. So we'd better be able to evaluate functions at places now, otherwise we have done something wrong with our name giving. So what I would like to do now is to formally define a way to evaluate functions at a place. So what we can do is, if we have an element from the function field and we pick a place, we want to define an evaluation map at P. So it will, as input, it would get a function field. Yeah, what would be its output? Well, if you would take a function on a curve and evaluate it at a point, you would get an element from the field of definition. But that is kind of lost now. That intuition really comes from the case where this F is algebraically closed. So the best we can do is try to find some fields where all these evaluations can land. And the thing that turns out to be the right thing to do is this. Yeah, so an evaluation map, it had better have the property that if I pick a function that happens to be in the place, it should give you 0. Yeah, because otherwise this whole way of building up the theory doesn't make sense. A place, we were intuitively thinking about it as the set of functions that vanish at a certain point. So we do the same thing here, we just mod out this P from the local ring, and then, yeah, if there's a pole, we need to add this symbol infinity. Yeah, so how is it now defined? Yeah, so we simply say that the evaluation of Z is equal to the residue class of Z modulo the place P if Z happens to be in the local ring, if it's defined, and otherwise we just say infinity. So this gives you then a way to formally evaluate functions at a place P. And just for the sake of notation, usually just write it like that. Yeah, so the functions we really can evaluate, but we end up in a slightly different field than you would expect. You end up in this field. So let us give this field a name. So it's called the field of residue or residue field of P. And we're just going to denote it by F sub P. Yeah, so that is the field of residues or residue field of a place P. Yeah, so again, if you're used to thinking in algebraically closed fields, then this is just always that algebraically closed field. But if we allow non-algebraically closed fields, this really can be something else. Yeah, as you can see here, if we look at the residue fields of the places we have been investigating here, so just in this particular case, if we look at f of this, sorry for the double index there, if we look at the residue field of this place here, this is going to be just a polynomial ring modulo that irreducible polynomial that was involved in defining it. So, in particular, you see this, if this px has degree larger than 1, it's really an extension field of this f, of this field of constants. And in this example we had up here, here it turns out that the residue field of this is going to be just f after all. So, apparently, we have now a way to discriminate between what kind of places we are looking at. Yeah, so there are some very simple irreducible polynomials, namely just x minus a constant, and for those you would just get f back again. But if p is an irreducible polynomial of higher degree, then this is going to be a proper extension field. And with that other example, the place at infinity, we just get f back after all. So a way to see the distinction between those two kind of behaviors is that we just define the degree of a place to be the extension degree. Now, one may ask, okay, in this particular example, this is always a finite number, but in fact, that's a lemma, it's always some finite number. So the degree is really just some positive integer. And just for future reference, if this degree turns out to be 1, which is the case in the example when we look at the place at infinity or at degree 1 irreducible polynomials, then we get rational places. Yeah, so that is just another way of saying that the degree is 1. Okay. So now we have some terminology in place. We have a function field, we have places on the function field, and several properties of it. The degree, we can evaluate functions in places. So we are kind of building up a theory here. Now let's see. So the next thing I will need later on to describe algebraic geometry codes is the notion of divisors. So a divisor, G, is simply a formal sum of places. Where this AP are in Z and the coefficient is going to be 0 for almost all places. Almost all meaning finitely many are non-zero. So if you listen to the first lecture today, this will sound very familiar because this is kind of a cycle in this language of function fields. Since it is a one-dimensional object, you don't have much choice there for the dimension. So you're going to take sums of zero-dimensional things. So it's a zero cycle if you wish. But the language I'm used to is called a divisor. Yeah, but that's the same idea. And just like this morning then, there's also a notion of equivalence of divisors. So let me try to describe how that works. Maybe I should first define a few things. So since we know what the degree of a place is, we can extend this by linearity to the degree of divisors, like that. And also there is a partial ordering. So if we have the second divisor, BP times P, and if for all places AP is less than or equal to B of P, we're going to say that G is less than or equal to H. So this is not a total ordering, a partial ordering only, which simply means that all the coefficients in G are less than or equal to the corresponding coefficients in H, a particular place. So we have that notion. And then what we can do is try to associate to some fundamental objects, for today functions, to associate to functions a divisor. Now I think this has a very natural interpretation in intersection theory, but let me just define it in the language of function fields now. So if I have a function not zero, I can define the divisor of a function by, I take a formal sum of places, and somehow I need a coefficient. And what I'm going to do is I take the valuation at P as coefficient. So is this really a divisor? That's not immediately clear, because there was this demand that AP is zero except for finitely many P's, but this is going to be the case. So a way to think about this again is that if we have a curve, a function defines another curve and it will intersect infinitely many points. And the function field analog is saying that this is actually a divisor. So more precisely, one can even show that if we look at the divisor of zeros, so if we now look at all the places where this function is zero, we get a divisor like this, and we can also look at the opposite, where the divisor is negative, where the valuation is negative. Then you get another divisor like this. And then, in fact, note that this is just another way of splitting this divisor Z into two parts, like this. And then there's a very basic lemma which tells you something about the degree of these two.
Plus is there minus?
This?
Yeah.
Now this Yeah. Thank you. So. Okay. Yes, thank you. Yeah. So there's a very basic lemma which tells you exactly what the degree of these two are. Yeah. So the lemma is that the degree of this Z0 is equal to this extension degree. So yeah, so then let me say that, let me exclude the constants there. So yeah, so even is this a finite number or not, that is not immediately clear. So we know that for any function field there exists some element x such that this is a finite extension. But in fact, that's an exercise. If you pick any z there, not a constant, assuming that f is the full constant field, then this will always be a finite number. Yeah, so this is in fact very precise, gives you very precise information about this degree. And well, the consequence is then that the degree of this z infinity, yeah, well, what is it? So, in fact, I could just have said, let's take the inverse function and then the zero, the positive part of that. That's exactly the same thing. But then it means that I should write a z inverse now, but that's going to generate exactly the same field. So this is exactly the same number. So what we in particular have is that the degree of any divisor like this is going to be 0. Yeah, so maybe should put 2 like that. The degree of a divisor coming from a function will have to be 0. And that is a very strong property. Should say that such divisors are called principal divisors. Okay, so just recap and then I stop. So I started by some geometric pictures. It was not much more than that. But I hope it gave you some intuition of what is going on in this function field language. These places are nothing but placeholders for points on a smooth projective curve. If you usually we take f to be algebraically closed because the thing turns out to be very nice in that case, but for future purposes we cannot do that because this is going to be a finite field later. And this is why we have some complications or maybe interesting phenomena going on. In particular, a way to measure that is the degree. So the degree, if it's 1, we say it's rational. If it is positive, it gives you an idea about the degree of non-rationality, so to say. I ended with divisors. So right now it's not so clear why I'm interested in those, but that will come in later when I'm talking about the Riemann-Roch theorem. So thank you for today.